So if I look at this guy, now watch, as I move along, here's the TNV. The unit tangent vector is purple. Unit normal vector is gold. And the binormal vector, I wish they would just put an NTV on there. That would have been great. But as it moves, now notice, the unit normal is which one again? The unit normal is the gold one, right?
Yeah.
What is true about that unit normal? What seems to be always true about the way it's pointing based on the curvature of my motion? Pointing in, and I think if I said pointing in, you guys would be cool with that. It's on the concave part, if you know lenses and mirrors and shit. It's always so. If I have a parabola, it's going to be pointing this way. It's going to be pointing inside the thing, not outside the thing. Are you guys with me? It's all right. Good. So it's pointing out of your spoon as you point it, not on the other underside of your spoon. Okay. The purple vector, of course, is doing what we know it should do. It's just pointing me in the direction that I'm actually traveling. And then the last thing that we created was really just to make a complete three-dimensional system. It's pointing that way. And I always think about like the unit normal vector as sort of, if I have something coming along, it reaches out and pulls it, so it kind of curves like this, or it pushes. You could think of it as pushing it too. It's totally up to you. So if you've taken any physics, it's sort of like a particle entering into a magnetic field. The magnetic field can just push it and make it curve. Or maybe if you haven't, then that doesn't matter. But it's okay. Just one more example to think of. Let's see what other curve they have for us to look at. I can also do that. This gets a little bit roller coasterish, but it's always interesting. We could follow the frame. Yeah. Anybody starting to feel sick? You can just look away. Yeah. I can't force you to look at it.
Dude, that was crazy.
I know. I love it. Here's a different curve. You can see the definition of this curve. So it's really, really freakadelic. Notice what's true about X, Y, and Z. They're all somehow, what would you say? Ooh, look at that. This gets really neat. Now watch. What happens right in here? Watch what happens.
It's crazy.
Oh, I can rotate this. Okay, cool. So there's the hidden piece that was happening right up there. Is that little knot. So if I'm in this ship and I'm like, okay, everything's going great, Houston, wait the all right, but if you do like a Google search for TNV frame, aeronautics or NASA or even submarines sometimes use this because they move, or airplanes, but very often it's space motion that you're talking about. You'll see how they use this kind of idea to just have because in space, like I said, there's no up, there's no down, so you define it based on how you're moving. That only kind of makes sense. So this is just an example of what those vectors are doing that you can calculate. This is what they're doing as they follow the motion of the particle or the ship or whatever it is. So what we're doing right now, I don't know if you guys notice, is we are just seeing what it is we can do with these basic things we learned back in chapter 12. This is all chapter 12 stuff, right? This is cross product and length and all that kind of stuff. And married with 180 stuff, derivatives and so forth. Okay, cool. I like it. So we're seeing what these things can do for us and how they can be used in real life. Okay, so if I remember, let me see. Let me send this to myself and then I'll... Yeah, there's CC. Can I write a note? There you go.
Just send it to us.
Okay, so I'll send that to you guys later. Even if you don't have the WebAssembly, you can still access this page, which is really, really, really nice, right? Because a lot of these animations make some of these concepts easier. I just kind of forgot earlier that you actually have access to this page. Okay, let me see. I think I'm gonna. At the bottom of page 907, what I didn't do yet is some of the more technical other ways to write kappa, the curvature. But I would highly recommend page 904 and 905 that you kind of read through that. We'll do those together next time. But they just put kappa into a form that works better in different situations. But it still has to be based on this. So any other form you want to put it in has to be based on this. And the last part of section 13.3 that we still have to talk about is some little bit weird stuff. And you're like, well, everything in this class is weird, Jeff, but there's stuff called the osculating plane. There's one that makes a little more sense, the normal plane. I can kind of imagine what that might be. The normal plane at a point to a curve, what that might mean. The osculating plane, there's no way in hell that word tells you what it's going to be, right? Yes, sir?
Is that like sine wave or?
No, not oscillating.
I thought you were like Mr.
Not oscillating. No, yeah, I like it. I love how you gave me that. All right, he needs a little help, but no. I think it's oscillating. It's not oscillating, it's osculating, yeah. That sounds like one to look up in a dictionary. And the nice thing about section 13.4, just looking ahead, is it's everything we've already done just in the context of a particle moving through space. So now when I take a derivative of r, it actually is going to be the velocity. When I find the magnitude of r prime, it would be the what? The speed. I like it. And then the acceleration is the second derivative and so forth. So 13.4 will actually be kind of nice. Stuff we've done already, just in a more a context you can see. That's enough for today. I'm going to let you guys out. It's a little early.
Right now I'm seeing this in class. Is there still a chance that I pull this class?
We can run some numbers. What'd you get on the test again?
75.
Okay.
And I realized I made some really bad mistakes in that test. Like stuff like I knew, but just not. Anyway, we'll take it off.